Let me introduce your presentation.
I shortened the title a bit.
Ah, good.
To conform with time constraints, so I took off the part.
So good afternoon, everyone. So we are about to start this session this afternoon. So you can ask questions using the Q&A button at any time, but the questions will be answered at the end of each presentation. So our first session is going to be presented by Amir Sagiv from Columbia University. And the title is Reversibility Loss in Nonlinear Optics. So please, Amir, go ahead, share your screen.
Thank you, Jaime. You see the screen? Is it fine now? Can you thumbs up if you can see it? Okay, good. Hi everyone. Good afternoon, good morning. When I organized this, when I applied to talk here, and I'm happy that I were accepted, I didn't think through the fact that I'll be in Oregon during the talk, and it's 5 a.m. So good morning or good night to you if you're in the same time zone as me. So this is a part of the work that I did with my former advisors in Tel Aviv University, Adit Kovsky and Gadi Filich, and with our good colleague at New Jersey Institute of Technology, Roy Goodman. And in the title, maybe in the abstract, there would be loss of phase, but we'll talk mostly about loss of reversibility to somehow conform with the time frame. And before I say something about reversibility loss, I should say something about the context. So reversibility loss is something that is ubiquitous and happens in a lot of systems. I want to focus today on a single system where it may be easier to track things and be concrete about what happens and how reversible systems can become irreversible. All right, let's see that in action. So just to fix notions, you don't have to be an expert optics person or expert physicist. We're talking about laser propagation. So think about extreme light, concentrated, high intensity that propagates through a medium which is, in the literature, you'll see it as kerr-medium, homogeneous kerr-medium, pretty much anything that is not vacuum and is homogeneous. So air, water, glass, various gases, various crystals, provided that the power of the laser is high enough, the medium nonlinearity kicks in and you'll see nonlinear propagation. So today we're not talking about anything that happens inside this box that emits laser light, but rather on the propagation through the medium. So before I say anything about reversibility, I should say something about what is reversibility, really, before I talk about its loss. So known setting, the setting that we know that happens in experiments and in simulations for, I would say, a few decades now, is that in high powers, two beams, so those are two beams, think about two of these boxes that I showed you before, pointed to the same geometric location, and when the beams meet, because of the nonlinearity, the beams fuse into a single intense beam. So two beams, those Y shapes that we'll see today in the talks about. All right. Now suppose you have a detector at the end of the propagation. So this is the distance of propagation, and this is a cross section of one plane. So here's a camera. So think about something maybe more sophisticated than this 1980s Canon, but something of that sort. You're recording everything that happened at the output. And now what you want to do is backpropagate. You want to image, really. The medium is homogeneous. It's non-lossy, so you would expect propagation to hold. So this is what you see, and now you're backpropagating. What would you expect to see? So there are two extreme options, so two cartoonish ends of the spectrum. One would be perfect reversal, right? So if this is what happened in forward propagation, you would expect in backward propagation the beam to split into two. Somehow that seems unlikely. We don't yet at this point know exactly to explain why unlikely. Just seem unlikely that a single beam will split into two. So the other extreme would be that a single beam will remain single beam forever. But now notice, even though this looks more plausible than this is not reversal, right? If this is happening, then reversal didn't work. And if the former happened, reversal did work. So which is it of the two? This is the question that we'll be talking about for the better part of this talk. Just again, to fix what are we doing? So this is a math talk, so we'll stick to one model. The one model that we'll be using is a nonlinear Schrödinger. It's a well-vetted, well-known model for nonlinear propagation. If you've never seen it before, don't worry, we'll not be diving too deep. It will be completely self-contained in terms of what you need to know about this equation. So let me introduce you to everyone here. There are transverse coordinates in R little b. So think about, for example, in those slides, these one. So there's one dimension. Time, quote unquote, is Z. So this is an interesting feature. We're thinking about light emitted from the laser and being propagating forward in the Z direction. So for all mathematical purposes, the Z direction is time. This is a timeless, in the physical sense, a timeless picture, but Z is time. The word Schrödinger appears here because of the mathematical form of the equation, but it's all classical physics. We're not talking about anything that happens due to uncertainties and quantum effects and so on and so forth. So everything here is inherently deterministic. We're solving for the electromagnetic field in the Maxwell, and there are a lot of nonlinearities that you could concern. So this is really, I would say, a remark for the aficionados of the NLS. If you know the NLS, then there are a lot of nonlinearities that we could consider here. I will consider today the cubic quintic nonlinearity. It's a very well-accepted one to model high-intensity lasers, but there are many other options that you could take. So again, close brackets. If you haven't seen it before, this wouldn't matter too much to you. If you know the NLS and you care about the details, this is mostly what I'll be using. Okay, so now I can show you, this is the NLS that we simulated before, and those are the two options where would the beam split in backward reversal or remain the same and reversal would be lost. All right. Just before, I'm teasing and saying what will happen, like why, many of you would ask, why would you care? Well, one of the reasons you would care is the application side. So I would say in the last decade or so ever since 2009, there has been a couple of works, even more than a couple really, of works that have said, people were saying, can we use nonlinearity to improve on imaging? Because reversal really is imaging, right? So imaging and reversal go hand in hand. You want the medium, you want the propagation to be reversible so you can recover the input from the output. So all these tasks, all these groups were thinking, can we improve imaging tasks? Can we improve imaging performance by using medium nonlinearity? So whether nonlinearity impedes or enables reversibility is really a fundamental question to those applications. And I would say it's also a fundamental question when we look at reversible systems. So here's the fundamental point of view. The fundamental point of view would have told you that this talk should end in slide 9, okay? So why should this talk end now? Because the NLS is invariant and what is called the phase conjugation or the time reversal transformation. So if you take Z to minus Z and you take psi to psi star, the complex conjugate, it's the same equation. You get the same equation. So what you should think about is you take the field envelope at ZF, you conjugate it, and then when you let it run forward, it is as if you would have let the equation run backward. This is actually what people do in laboratory settings, all right? So the NLS is reversible. It's not like the heat equation. There's no loss of information, so end of story. Equation is reversible and we can end the talk. But I was given a few more minutes, so allow me to entertain you with what happens between those 3 points and the end of the slide. So what can go wrong in a system which is in principle completely reversible. All right. So here's our Y shape, the beam fusion setting that we talked about before. and here is what the detector sees. So I'm plotting here only absolute value squared. So this is, in optic setting, would be intensity, for example. And what you see is a strong beam in the center, two little lobes on the side, and pretty much nothing at the end. Okay. Had you had an infinite detector, then by the time reversal, or the reversal, or the phase conjugation symmetry, reversal would have worked. So now this is not Photoshop, this is actual simulation, okay? So really what goes in comes out, you can recover the input from the output. Fine. Now, suppose you don't have an infinite detector, as no one has an infinite detector, but you have a very, very large detector. So it's somewhere in the gray area. It's 13 times, if I remember the number correctly, 13 times larger than the width of the main lobe. So it's quite large. It's realistically large. What would then happen? So you truncate, mathematically, you really truncate everything outside of this detector. And what you'll see is no reversal, loss of reversibility. The beam doesn't split. You do not recover the two incoming beam. All right. Is this, so now you would say maybe this is something special for the truncation. So now let me try to show you that even if you perturb, if you have an imperfect detector in another way, it would still not work. So here's an infinite detector. Again, I idealize in one respect. So it's an infinite in space, but it's finite in bandwidth. What do I mean? I take the Fourier transform, but instead of taking the full Fourier transform, I take just some frequencies. So think about a digital detector that cannot resolve very high frequencies, or think about far field imaging, or what have you. Again, when you do that and you take a very wide, and again, the parameters are in the paper, you lose reversibility, okay? So you take a very, very wide frequency range and you lose reversibility. It will happen again if you discretize. Here I am discretizing. So take a look. This is a zoom in. Remember, earlier I showed you between 0 and 13 or 40. Now I show between 0 and 1. So the red lines is how we discretize. If you'd look at this picture, it would look like a pretty good discretization, a pretty fine discretization. And still, when you apply it, reversibility is lost. And this is, I would say, after a lot of simulation, pretty robust. It's not a numeric artifact. It's really a property of the discretization. Okay. So far, I just give you anecdotes. So let's try to summarize when is reversibility lost in these settings. So I'm going to stick to one example, and that's the finite detector. But everything I said can be applied to the other imperfections, and imperfections that I haven't shown you in this slide, but are in the paper if you're interested. So let's see. How bad is the perturbation, right? When you apply perturbation and you see it has a dramatic effect, you would ask yourself, is it a bad perturbation? Is it a large one? In terms of the intensity, it's 1/10 of the percent. We threw away 1/10 of the percent of the total intensity. So it's pretty small. It's something that you wouldn't have seen in an actual photo unless you were really, really careful to look at. We took out, it's an L2 conservative system. So we took out 2% of the total L2 square. You would say, well, the well-posedness, we know PDEs. The well-posedness theory of this equation is maybe in H1. H1 also includes some information about the phase. Well, we took out more than 2%, but it's still 7%. It's not so much. If you talk to experimentalists, those are the kind of things that get thrown away in experiment just due to noise, just due to imperfections with the measurement system. Those are not high numbers of error at all. So we can say now with some certainty that if you just track the amount of loss of the L2 norm, or the H1 norm, that would not predict very well loss of reversibility. That would not indicate to you that you are roaming around the turf where you no longer have reversibility guaranteed to you. Okay, so you might have asked yourself, well, you told me that 7% and 2% are not large numbers. How can I know that those are not large numbers? There's not There's no rule of physics that tells you what is large or small. It's a matter of sensibility. It's a matter of intuition. So let me show you that if you run exact same perturbation that you've run before, so the exact same spatial truncation, but instead of running backward, you would run forward, then there would be no noticeable effect to this truncation. So in other words, you put the detector, but instead of running backward, you run forward. So this is a thought experiment more than an actual thing that you would do in the lab, but you could do it. And you see that there's no discernible effect to the truncation, meaning this perturbation is small when you think about forward propagation, and it is large, it is dramatic when you do backward propagation. Okay, that means that somehow, even though every initial condition doesn't care if you run the equation backward or forward, to an ensemble of conditions, to in a perturbative sense, there is a difference between forward and backward. So now let's explain what we saw so far. Okay, so to talk about reversibility, it will be easier to talk first about the backward dynamics. So here is the forward propagation that we saw before. And if you want to interpret what happens here, it's a single stable solitary wave that goes out after two stable beams went in. And now when we run the backward dynamics, when we reverse it, a single stable solitary wave splits into two stable solitary waves. So there is a decision, quote unquote. Of course, everything here is completely deterministic. There is a decision, there is an effect that happens that makes it jump from one stable state to another. And if you want to understand it, it's in the radiation. The radiation decides. Now, of course, the radiation doesn't decide, but what really happens is when the beam fuse, there is a certain pattern of radiation that goes out. And if you want to reverse, if you want to jump from a single stable state to another stable state, you need to have that tailored radiation from the forward dynamics. The moment you perturb it, the moment you change it, you lose reversibility. It's a very gentle thing. You have, basically, it's a dispersive equation. Radiation comes from infinity. You need to be very, very sensitive to this radiation. Now, the radiation is low in amplitude, low in AL2 norm, and low in H1 norm. So all those things that we said cannot indicate what is happening in the tails of the system. So all the interesting stuff, you might say, are happening here and here, and not in the center where the actions seem to happen. All right. So if you want to see it even better, here's something we can do. We can, you remember we had the detector that has a finite size. We can now start to enlarge it, start to expand it further and further and further. So if you expand it further enough, certainly you get splitting. It's not perfect reversal, but okay. What happens in between? So what would happen in between is that you will see a phase transition. So you'd see those ellipses that are elongating and elongating. So again, think of those ellipses. You're looking at the beam from above. You're above, looking down, and you see a beam. You see the radiation coming to the beam, trying to split it, but somehow, since you don't have the right radiation, since you truncated a very, very, very small portion of it, you see this starting of a split and then failure to split and return to a single beam. All right, so that happens again and again and again, and you really see that the radiation is clear. In the paper, you'll see we also blocked part of it, and it seems really that you need to be very, very careful about radiation, and careful, I would say, in a way that is not realistic to an experiment. So in experiment, if you look at the center beam, you are not likely to see very, very far from the center. You're not likely to see portion of a % intensity at a distance of 10-fold from the width of the beam. Okay. So when we do the spatial truncation, we have this phase transition. And so you can say the following. Suppose I fix ZF, the final distance in which I do the measurement and reversal, and I do the truncation. So with every ZF, there is what we call XTH, X threshold, okay? The size of a detector, and you can think about any perturbation that you like, but the size of the detector above which you get reversibility and below which you don't get. And now that number generically might change with ZF. Okay. What would we expect this number? How do we expect this number to behave with the distance? So a naive thing would be to say the radiation diffracts. It goes wider and wider and wider. So we would expect that the threshold, just to capture the same amount of radiation, we would have to take a wider and wider and wider detector. So we would expect X threshold to increase with ZF and loss of reversibility to increase with the distance. And that's true. That really happens. So we did simulations, and you see that the minimal size of detector you need to take for reversibility to hold does increase with the distance. But what you also see is that your sensitivity in terms of norms, in terms of L2 or H1 norm, increases. So if you lose less at a larger distance, you might still lose reversibility. These two figures indicate that it's not only that as you go further and further, you need to capture the same amount of radiation, but rather that you need to capture more as you go further and further. We don't know to explain it, and we also don't know whether those two curves go to zero, right? Because numerically, it's really hard to see whether they go to zero or not as you go to very large distances. I would say that it's interesting, if any of you are doing PDEs or thinking about those sort of problems, it's an interesting PDE problem that one wants to study. It has to do a lot with the well-posedness theory of the NLS. And if it doesn't go to zero, by the way, then it goes to some quantity, which is some intrinsic value. So really, that's an open question, and I'm just putting it out there for us to think. So we know reversibility is lost, but is there a minimal reversibility environment? Or if you go further enough, you can always guarantee it with something. I don't know. I have more time, right, Jaime? 5 minutes? Fantastic. Yeah, okay. So far I told you all the NLS and the NLS and the NLS. I want to show you now that what we saw so far has nothing to do with the NLS. It's not about nonlinear optics. It's not about the Schrödinger equation. So if you're coming from neuroscience or from fluid dynamics or from what have you, I want to convince you that you saw something today that should interest you, and maybe you can look at in your own respective systems of interest. So this is the 5-4 equation that we'll be talking about to the end of the talk today. And what we saw so far can be abstracted to sort of recipe to loss of reversibility. Remember, if we have a system without guaranteed reversibility, there's nothing to talk about, right? If this was the heat equation, well, forget about it. Reversibility is lost anyway. Here, there's a reversibility system, a reversible system, I'm sorry, where one, there's a stable state, the solitary wave, the single beam that went out is stable. You let it propagate forever, it will propagate forever, no problem. But the other ingredient to the recipe is that there's reversal information. There is a way to exit that stable state when you go backward, but it depends on the very, very delicate radiation. So it depends really on things that are hard to measure and easy to perturb. And now I want to show it to you in the 5-4. So here's the 5-4 equation. If you've never seen it before, don't worry about it. It slightly looks like the Klein-Gordon equation, but it has a nonlinear term. It has a reversal transformation. Take t to minus t, the same equation. So there are no forward dynamics and no backward dynamics. It has solutions that look like kinks. They're analytic solutions, they're stable, and they have a parameter. And what you'll see is that a kink and an anti-kink can go forward in time and then fuse into, well, not a single thing, but this, let's call it for today, a train of blobs. And again, in the paper, there is more serious discussion of what these are. Fine, if you reverse it, then this train of blobs suddenly split into a kink and anti-kink. That's to be expected. There is a reversal symmetry. But again, if you perturb the radiation, you lose it. And again, we do the analysis, we do the numbers. Those are small numbers of intensity that are being truncated away. So again, the same phenomena really happened in the 5-4 equation. In the phi-4 equation, more interesting things happen. So for example, loss or gaining of reversibility depends very, very, very delicately in some of the parameters here. So you see this is really a small, almost non-physical difference between the parameters, but here you have reversibility and here you don't. So again, things are very, very delicate. Even the dependence on the radiation itself is delicate. Finally, I want to tell you that even though in both of these examples that happen in different equations, we have the fusion of two structures, right? So two solitary waves fusing into a single beam, a kink and an anti-kink fusing into a train of blobs. Again, I want to show you this as a general thing. So this has nothing to do with the fusion of two structures into one. We can have loss of reversibility in a single structure. So I'm going back to the NLS. Now it's the 2D. So let me open parenthesis. If you know the NLS well, then you know that in 2D you should have collapse. I'm adding the quintic, so we'll have global existence, but you can think about it physically as collapse. Close parenthesis. This is the 2D NLS, and one of the things that happens is that you start with a wide beam, and it becomes a narrow, very intense beam. So you can see here, you start at low intensity, and this is the on axis. You see that very fast, you become very, very intense, 30 times more intense, really. Sorry, 1,000 times more intense, 30 in absolute value. And this is what you see here. You see something weak becomes very intense and very narrow. And you can reverse it, of course. And by now, you wouldn't be surprised when I show you the third slide. You truncate very, very, very far, and you get non-reversal. Here, again, you will get reversal if you wait long enough, but you wouldn't get the perfect reversal at z equals 0. Okay? So again, same example, same phenomena, but at a very different example and very different settings. Let me conclude with the last 2 slides and ask you now, this is a dynamics workshop, a dynamics conference. So there's a dynamical question here that goes beyond the optical questions and the optical implications. Here are 2 pictures of NLS solutions, and I didn't put the time axis on neither of them. And you know, in birthday, kids play the game where they put a blindfold and they have to put the donkey tail with a pin. So I'm asking you now to put the z-axis on either on the going to the right or going to the left. So which of these 2 pictures is forward in time dynamics and which of these 2 pictures is backward in time dynamics? This is in a strict mathematical sense, this is a nonsense question, right? It's a nonsense question because there's no forward and backward NLS. It's the same equation. There's no forward and backward wave equation. It's the same equation. This is a mathematically valid NLS solution, and this is a mathematically valid NLS solution. We can point the arrow of time to the right and to the left, and it will be the same. But we've learned something in this talk, hopefully, and that the left picture, so I don't know what's left and right when you look at the slide. So this picture has outgoing radiation. It radiates and it's stable under perturbation. You change slightly the radiation, you change slightly even the central beam, and you pretty much get the same dynamics. Here, it is radiating inward and it's unstable under the perturbation. So that gives us a sense of arrow of time in a system that didn't have it a priori. So when you don't think about a single solution, but rather on an ensemble in a perturbative sense, you do get an arrow of time. So it's much like the thermodynamical systems where every solution can be directed backward in time, propagated backward, and it works perfectly well. But when you start to consider perturbations and you consider a lot of initial conditions and what is likely or unlikely to happen, then there is suddenly a thermodynamically irreversible dynamics. And there is an arrow of time which considers probability and not just the deterministic dynamics. So I think this is interesting, and I think this is something that goes way beyond the concrete setting that we consider today. Yeah, the paper is out in Physica D. I advise you all to go read it if you want, and I'll be happy to take questions now.
Many thanks, Amir, for your beautiful presentation. We don't have questions, but let me ask a fast question. So, can you make bound state of more than 2 pulses?
So 3 of them fusing together.
Yeah.
The short answer is yes, people are doing it. It's again more delicate because, for example, if you have 3 and you perturb it slightly that the first 2 are meeting before the third one, then it's really 2 fusing and another 2 fusing. But yes, the answer is yes. And there have been experiments with that, and there has been applications that are trying to do it. There's a lot of problems in doing it in a controlled way, but the short answer is yes.
Yeah, so the pulse can remember the number of beams that were used for the...
Right, somehow, but remembers it very weakly. Very weakly. It remembers it in the radiation.
Great. So many thanks, Amir.
Thank you, thank you. Oh, there's been a question.
There is another question. Can you read the...
Yeah, I can.
Question?
I can read it.
Aloud,
I'll
please.
read it out loud. Thank you. Would it be possible to perturb the system slightly as it propagates forward in time to improve its reversibility? That's an excellent question, actually. Well, first, it's an excellent question because I don't know the answer, but let me tell you more why this is an excellent question. Because really we know that, we know that this would be useful, right? Because we know this would not only be something to do. So here's a question. If the medium has imperfections, so that's a way to perturb the system. So you don't perturb the inputs, rather as perturb the medium. And we know somehow that reversibility in linear systems can become even more robust when you have imperfections in the medium or some statistical noise in the medium and so on. You can use correlations, you can use all sorts of things. So we know what happens in linear systems in this case, no idea what happens in nonlinear systems.